welcome everybody. So far in acids and bases, we've talked about a weak versus strong acid. We've talked about definitions, Bronsted, Lowry, Arrhenius. We've talked about conjugate acid and base pairs. We've also talked about how to calculate pH, POH, H plus, OH minus. We've also discussed weak versus strong acids, and we have discussed how to use Kas to solve for pH, or how to use pH to solve for Ka or Kb. What I wanted to talk to you about is a relationship between acids and bases that are conjugate pairs of one another. And what happens is when you have an acid that is weak, it produces H3O+, and I show that here in step 1. Step 1 shows you HA reacting with water, producing H3O+. But what I failed to mention so far, and what is actually really important that you take note of, is that A- actually has its own reactivity. That A- will react with H2O, and it will almost go in reverse. It will form HA again, and when it forms HA, it also forms OH-. So the top reaction here has HA as an acid producing H3O+, and the bottom reaction here has A- as a base producing OH-. And so both of these reactions occur, but the question is, and what we need to really figure out is, well, which reaction's occurring more, and how is that affecting the pH overall? So here are some things to consider. First of all, most of the, if we dissolve HA, and this should be HA here, if we dissolve HA, then most of it's going to exist as HA, because its Ka is small to begin with. Very little will dissociate into H3O+ and A-. Now you then have a very small amount of A- available, and even less of that is going to react with water to form OH-. And in this case, and in pretty much all cases where you have a weak acid, the H3O+ generated is a lot more than the OH-, and the solution is acidic. But what if I were to have a situation where I were to take some, instead of HA, what if I were to take some, NaA? What if I were to just have NaA? And in this case, I then switch to NaF as a specific example. Now, if I have NaF and I take that and I put it into water, well, the first thing that happens is we get a breakup of the Na and the F, and it produces F-. The Na is a spectator, so I just leave it out. Now this F- is then going to react with the water, just like the A- did up here in step 2. The F- down here now reacts with the water, and look at what we get. We get OH-. So this is called an anion of a weak acid acting as a base. Let's think about that. HF is the acid, or HA is the acid. It produces A- or F- to be specific. And then that anion, that A-, that F-, that acetate minus, whatever it is, that anion will go off and it will react with the water and it will produce hydroxide. Now in this case here, we dissolved NaF. We didn't dissolve HF. And so because of that, the NaF was in high concentration. The F- was in high concentration. The amount of OH- that you produce is going to be, more than any HF that occurs, producing H3O+. So in this case down here, we're going to have more hydroxide than hydronium. Now, if I wanted to, I could include that HF reacting with water, but again, it will get to the same point that the NaF is the major source of F-. That has, a huge amount of that compared to any HF that's going to ionize and form H3O+. Now the thing is that we can relate the HA and its activity to A-, and we can relate these and see which one's stronger. And we can do that by relating the Ka and the Kb to one another. And the way it works is really kind of cool. I want to show you that down here. If you go back to the reactions that I put up above, the HA reacted with the water and it formed H3O+ and A-. We have that from above. The A- also will react with water in the same solution and produce OH-. Now, if I add these two equations together, I get something that should look familiar to you. It's the autoionization of water. Now remember, I'm taking these two equations and I'm adding them together, added up. This has a Ka, this has a Kb. When you add equations, remember what you do to the K values. You don't add them, you multiply them. And that's what we get here. We have Ka times Kb equals, well, Kw. This is my Kw. So Ka times Kb, at least at 25 degrees Celsius, will always equal the Kw. And this is really neat, and I show you the work for how that goes down here. If I wrote a Ka, it would look like this. If I wrote the Kb, it would look like this. And then when you cross out all the like terms, so HA cross out with HA, A minus cross out with A minus, you're left with just what's in the Kw, H3O plus OH minus yields Kw. But this equation right here, this is what you really have to keep an eye on and know. And so you can see from above, like if we were to have HF, for example, HF, I know, has a Ka equal to 1 times 10 to the negative 4th. And that means that F minus, I could figure out its Kb, and it's 1 times 10 to the negative 10th. So that combination of the Ka and the Kb, that tells me what's stronger. I see that stronger is the acid. And so even though there is some A minus or F minus produced when HA reacts with the water, the A minus, or in this case the F minus, it doesn't react very much with the water. And that's why you have an acidic solution with HF. And you don't really consider the F minus very much because its dissociation into H3O into OH minus, given its initial concentration that was produced, is going to be very low. It's not going to affect the pH. This will come back to us, though, when we think about buffers. And we'll do that in the next video. But here's a problem where you have, Ka and Kb. And so what I'd like you to do is I'd like you to try this out. See if you could figure it out. It's not just a straight up Ka problem. Remember, you have this salt here. You should write out the reaction. You should see what's happening. Think about what we did on the previous slide too, relating Ka to Kb. Alright, thanks so much for watching. Next time we're going to do buffers. This is where things get really interesting. This is where things get difficult. Alright, thank you.